Hello, everyone. Welcome to CPE 517-WS Digital and Computer System Architecture course. I'm Professor Han Liu. This is part one of lecture 4. It mainly talks about a 5-stage pipeline. So the first one is 5-stage instruction workflow. Okay. So first, some logistics. For this class, we use slides from David Patterson. And also, Sen Lipsati and Howie, all the credits goes to the original author and all the errors are mine. Reordering and modifications might be made due to requirement. Okay, the 5-stage pipeline of the MIPS data flow or any data flow would be like this, right? Okay. We have like instruction fetch, instruction decoding, or register fetch, execution or address calculation, memory access, and write back. Okay. For the first step is instruction fetch. Instruction fetch means we fetch the instruction, right? When you execute the instruction, you have to fetch it. Like in last lecture, we mentioned about in RISC-V. You have the 010101 plus 32 bit, like bit stream. You have to fetch them. And then once you fetch them, you basically get an address, right? Use the address to go to memory and fetch the instruction out. And also you add the instruction by 4 bytes, that's 32 bits. So that's the next instruction is PC or program counter, which means it's the potentially next instruction. But it's not always, because you can have jump instructions or branch instructions, which we can talk about later. Okay. And then the second step is doing instruction decoding. Basically, you get the resource register 1, resource register 2, and destination register. And also you could potentially have the immediate. Then you do sign extend, because the immediate is shorter than 32 bits, because total of the register 1, register RS1, RS2, and RD, potentially immediate and also opcode, together it's 32 bits. So the immediate alone definitely is shorter than 32 bits. That's why we have to do signed extension. And in this stage, you basically use the register ID to fetch the value for the register, right? Is the RD, RS, RT, and you got the instruction opcode, like what instruction you are trying to execute, like addition, subtraction, multiplication, division, branching, etc. The next instruction would be, the next step would be the execution step. You use ALU. For those of you who don't know what is ALU, it is actually arithmetic and logic, AL unit, right? A is arithmetic, L is logic, U is unit. MUX is the multiplexer, which means you can either use the output from the register file of the source, 2 sources, or you can use the PC, or you can use the immediate, whichever you feel that is the correct one. You choose from one of them as the input for the ALU. And then this equals to 0 or not is a BEQ, right? Branching, if it's equal to 0. And then the output goes to the memory, okay? Memory step is mainly for memory access, including load and store. So that's why we have the load memory. Let's see, what do we have? Load memory data here, right? So, and also in the memory access, we might also output the PC of next instruction if it's a branch instruction. The last step would be write back. Write back means you get the value from this pipeline and you write it back to the register, right? It's in the pipeline, so which is not in the destination register. So we have to write it back to the register. Like for example, is a destination register. So taking all of them together, you have instruction fetch. It fetches a new instruction every cycle. The current PC is the index or address to the instruction memory. We increment the PC at the end of the cycle. We'll assume there's no branch for right now. That's why we have this adder for 4. We write the values of interest to pipeline. Like the instructions are ready to pipeline register, which we're going to talk about later. Instruction bits are used for letter decoding, the instruction decoding, and PC plus 4 is for letter instruction fetch, right? Instruction decoding actually read the instruction bit stream from the IFID pipeline register, like from here, to get instruction bits. We decode the instruction to generate the register RS1, RS2, RD, and immediate. Then the output of this is written to the instruction decoding / execution pipeline register. You got a control instruction, RD instruction, immediates, offsets, contents of RA and RB or R1, R2, sorry, RS1 and RS2. And you also have the PC plus 4 for the computing and branching. Execution instruction, execution stage probably is the most, is the desire of this 5-stage pipeline because you want to execute something, right? So the goal of the 5-stage pipeline is mainly execution. On every cycle, it reads from the between ID and execute this register file, pipeline register to get values and control bits, performs the ALU operations like addition, multiplication, division, whatever you can think of. Compute targets. For instance, if it's a branch instruction, you can do PC plus 4 plus offsets. Or you decide if jump or not, or branch should be taken. We write the values of interest to pipeline of this execution memory access. Value in this case is memory store or instruction if it's for memory access, okay? For the memory access, every cycle we do read from the mem and mem and write back pipeline register to get values and control bits. We perform memory load, store if needed, write values. So here's a little bit wrong here. It's supposed to be read from execute. / mem, right? It's from the prior. Pipeline register to get the values and control bits, okay? And perform memory load store if needed. The address is the ALU results here for the store. Read or load. Write values of interest to pipeline register, or basically once you finish, you write it back, right? And then we have the control information, RD index, results of the memory operation, and then pass the results of the ALU back to the right back. In the write back, every cycle for loading instruction, we write the loading data to the register. For ALE instruction, we write a calculated result to the register. So putting all of them together, you can see on the top, we have instruction fetch, instruction decoding, execution, memory access, write back. In the bottom, we tell you how each line perform what, right? So the first one is you get the instruction, okay, from the memory, and then the PC+4, this all instructions does that. And then for the instruction decoding, what the instruction has to do that. So you basically get the read some value from the register, source, register, destination. And then you put it into a pipeline register of A and B, you do sign and extend it, okay? And then in the execution phase, you have either register immediate, right, execution, or register execution. For load instruction, you have to calculate the address potentially. And then for branch instruction, you have to calculate the where is the branch, right? Pass it down. And then for jump instruction, you also have to jump to where, the address. Memory access and write back, it depends upon, it depends upon the instruction. If it is register, immediate register operation, you directly just pass whatever results you have here to here, okay? And if it is load instruction, you have to actually use this memory data access or load memory access or store similarly. You have to use this load memory data abstract data function unit or memory data function unit to either read data from this memory to register, or you write data from register to memory. But when you load, you actually pass the memory instruction, pass the value whichever you accessed from a memory to the write back register, okay? This is write back register. And then in write back phase, if it is RI or RR, you pass the value from the write back register to the real registers, basically from the pipeline register to the typical CPU register. Similarly, for this memory access, you also do that. You basically write the write back from the write back register of the 5-stage pipeline to the general purpose register. Okay. So I think taking all of them together, we do want to here we want to review what are these lines, what does these lines mean. So I feel it's important. We want to go through this again, try to make sense of all of the lines. For instance, we use the PC as the address, go to memory, fetch the instruction, right? This is the main goal of this stage. And then once we have the address, we also add the address by 4 in order to prepare the potential next PC, right? Once you have the instruction bits, in instruction decode, you decode potentially source 1, source 2, destination, and the immediate, okay? Once you have the source 1, source 2, and destination, you use this values as index, go to register file, which is like a hardware array. You index the specific registers, fetch the value out of it, right? Get here. And then the PC is also passed down from the instruction decoding to potentially the calculation. In the calculation, you use, assuming you have 2 register sources, RS1, RS2. This is a very typical case. You do ALU calculation, pass it on to the load, So for this one, it's most complicated. It can be register immediate, which means you have one as a register, right? Let's see here. Okay, assuming, assuming you take this and this, so it actually goes here and go here, right? So this is how, like the typical case would be of RI. RR would be these two cases. For the load instruction, it could be the A, which is one of the address, right? So you were to get RS1, for instance, and then plus the immediate. Okay. So it's like this, and the immediate. Together, you calculate the loading instructions memory address, right? Branch, for branching, you use the PC here. Oh, sorry, let me change the color. So you use basically this and the immediate, right? This is how you understand it. And for jump, you directly use the jump address to pass down to PC, like here. Okay. Like, I think I can use another color, like this. Okay. And then once you finish this, so for the memory access, you can either have load or store. For store, you directly store the value here. So you don't have anything pass on, right? But for load, you load the data from memory and pass it on to the register file, okay? So basically this is a load. You don't have anything passed on to register. Sorry, this is store. So you don't have anything passed on to write back. But for load, here, right? You do have things passed on to write back register. In write back, some of you might have questions. Like, what does it mean by write back? I already have memory access. Sounds to me write back is writing back to memory. No, write back is whatever you have in this pipeline register here, okay? Like the pass down in the pipeline register, right? It's not in the register file. It's in the pipeline. So what you're gonna have to do is you have to write it back to the register file. That's what we mean by write back, because later on you're gonna access this register file again in the next instruction, okay? Okay. So putting all of them together, we see that this 5-stage pipeline actually is pretty general purpose, right? So for all instructions, you have to fetch, you have to decode. Sorry. You have to decode. You have to pretty much write a lot of them. And then when it goes to execution, memory access, write back is more like a special case. Like different instructions might have different function units, or even some instructions might not need write back or memory access. But pretty much all the instructions has to somehow fall into this five-stage pipelines. I have to be honest, this is the most important. This is the most important concept of the computer architecture for the 5-stage pipeline. And next lecture, we're going to talk about how to do staged like pipeline. Right now it's staged, right? So you have one stage, second, third, fourth, fifth stage. And then how do you pipeline them? Like different stages can be executed at different time cycles simultaneously. Okay. Okay, we're going to talk about that next lecture. All right.